Welcome back. I'm Dr. Nuroshu. A one-sentence preview of this lecture will be how to classify a target variable with no attribute, one attribute, or multiple attributes. To answer these three questions, we'll discuss the following topics sequentially: confusion matrix, entropy, information gain, attribute selection, and decision tree induction. Let's go straight to an example. We drew a sample of 100 members from each of 3 credit card issuers, say Bank 1, Bank 2, and Bank 3. We look at these 300 people's performance windows in the last 2 years. And here is the distribution in terms of their target variable values. In Bank 1, out of 100 members, 90 of them are good accounts, 10 are bad accounts, 60 are good accounts, 40 are bad accounts in Bank 2. In Bank 3, 10 are good accounts, 90 are bad accounts. Now, given only the knowledge of the target variable, if you were to classify a new car applicant to each of these 3 banks without any other attributes, what would be your guess? A similar example is to guess a coin toss. If you are told the coin is biased and it lands at heads more often than tails, and if you are to guess how it will land next, what is your guess? Now, pause and think about it for a second. In the coin toss example, you guess heads, right? Similarly, not knowing any other attributes on an applicant, your best decision rules or guess will be to go with the majority. Therefore, our decision rules should be: for Bank 1, all future applicants are good accounts. For Bank 2, all future applicants are good accounts. For Bank 3, all future applicants are bad accounts. Before we rush to apply these rules on the real future applicants, let's look at if we can apply them on the existing data set to see how well or how badly they predict. So in actual outcomes, each member will belong to either good or bad. If we apply those decision rules, then again each member will belong to either good or bad in prediction. So if we create this 2x2 matrix along the actual dimension and predicted dimension, then each member will fall into one and only one of those 4 cells here. So we call this type of matrix confusion matrix. The correct prediction are those members that fall into this cell and this cell, which is called the main diagonal cells, i.e. from top left to bottom right. Confusion matrix is an extremely important tool in predictive modeling. So what we have here is the standard representation, but there are many other different ways of representing the same information. For example, in the software Weka, the confusion matrix is represented slightly different. So I'm going to work out both matrices and define the accuracy for prediction for Bank 1. The reason the confusion matrix is called a confusion matrix is because it captures how the prediction confused actual bads with actual goods. But confusion matrix itself can be quite confusing to learn. So I'm going to show you step by step how to fill out the matrix. Let's reiterate the meaning of each of these 4 cells. So this cell should capture the members who are actually embed account and at the same time predicted as an embed account. Therefore, that will be a correct prediction. These cells are the actual good accounts, but are mistakenly as bad accounts. Therefore, it will be an error here. In these cells, these are the actual bad accounts, but again, mistakenly predicted as good accounts. Another error. This cell captures the members who are actual good accounts and correctly predicted as good accounts. So once you again understand the meaning of these 4 cells, then you know, for example, in bank 1, the actual good accounts, these 2 cells should add to 90. And these 2 cells should add up to the actual bad accounts, which is 10. And the rule that we apply for bank 1 says all future applicants are good accounts. Therefore, we would predict all 100 members as good accounts. Therefore, these 2 cells should add to 100. That means these 2 cells would add to 0. Therefore, we know the value of these 2 cells should both be zeros. And since these 2 cells should add to 10, therefore this will be 10. Similarly, this should be 90. Now let's see if we can figure out how to capture the same information with the Weka representation of confusion matrix. Notice in this case, this dimension is the actual dimension, and this dimension is the predicted dimension. So here, how many goods do we have for bank 1? We have again 90s. We have 10 bads. So out of the 90s, how many of them are classified as good account? Again, A represents good account here, therefore here in this dimension A also represents good account. Remember, according to this rule, we classify everyone as good accounts. Therefore, of course, these 90 people are classified as good accounts, and therefore 0 are classified as bad account. The same rule applied to these 10 actual bad accounts. All of them are classified as good account, in this case represented as A, and 0 as bad account. So again, here you have it. You have 2 ways to capture the same information. Now I'm going to define the accuracy of prediction based on the confusion matrix. Again, as I said earlier, only those members who are falling into this and these cells are the correct prediction. Therefore, I can define accuracy as number of members or instances falling into the 2 diagonal cells divided by total numbers. That would be 90 divided by 100. So that gives me 90% accuracy for prediction, applying rule number 1 on bank 1. Now I want you to pause the video and get out a piece of paper to follow my example to produce the confusion matrix for bank 2 and bank 3, both in the standard representation and the Weka representation, and also calculate their accuracy in terms of prediction. Make sure you actually do it before proceeding with this lecture. Now make sure you get the same results as shown here. So we apply the same decision rules, i.e. to go with the majority on all 3 banks with no attribute available. We achieve the same accuracy for bank 1 and bank 3 at 90%, but we achieve a much poorer accuracy for bank 2 at 60%. Now pause and ponder why this is the case, and think of how this might provide insight as to how to measure the predictiveness of attributes when they become available. So instead of using a pie chart that we used earlier, we can represent the distribution of target variable values among those 3 banks in a different way, like this. We represent each member as a dot. A green dot indicates a good account. A red dot indicates a bad account. So you can tell bank 1 and bank 3 are a lot purer. By comparison, bank 2 is a lot more mixed. So it's reasonable to derive an observation such as this one. The more mixed, i.e. the higher the impurity, which again can be considered or equated to higher uncertainty about the target variable, the higher the difficulty to predict. Therefore, the lower the accuracy from prediction by applying the same exact prediction rules. Another important insight that we can derive from this observation is a predictive attribute should help to reduce the impurity of the target variable. Therefore, we can increase the accuracy of prediction. Another profound insight that we can derive from this observation is if we can quantify the impurity of a target variable, then the amount of impurity that an attribute can reduce on the target variable should measure its information on the target variable. So what do I mean by quantifying impurity? It means I want to associate a numeric value to indicate the degree of impurity of a target variable. Intuitively, the highest degree of impurity will happen when there are 50% bads and 50% goods. Also, bank 1 and bank 3, despite they have opposite composition in terms of goods and bads, they should have identical degree of impurity. So now imagine if we increase the percentage of bad from 10 slowly by turning this edge clockwise this way. So the impurity should increase first, and it should max out at 50%, and then it should decrease slowly, and it should decrease to the same value when the percentage of bad gets to 90%. Now we are encountering another important terminology in data science, entropy. So entropy is the degree of impurity. Entropy is one of the many ways of quantifying impurity. Essentially, it's the following formula. So in this formula, P sub B is the percentage of bad accounts. P sub G is the percentage of good accounts. And since PG equal to 1 minus PB for binary target variables, we can replace PG in this expression with 1 minus PB to arrive at this expression. And these two expressions are equivalent to each other. This one is slightly easier to use because you only have 1% here. So now let me calculate the entropy of bank 1 by using this formula as an example. For bank 1, the probability of bad is 10 out of 100, which is 10% or 0.1. So I just plug in 0.1 in this formula, replacing PB. So if your calculation works out correctly, you should also arrive at this number, 0.469. So now I can calculate a sequence of PB value that increase from 0% to 100%, like we described earlier in the previous slide. And we can plot their corresponding entropy values in the scatter plot, like this one. So the x-axis is the probability of bad values ranging from 0 to 1. And the y-axis is the entropy. So you can see the entropy starts from 0 when probability of bad equal to 0. And it increases slowly and max out at PB equal to 0.5. Then it drops back down to 0 when PB equal to 1, which is exactly what we expect an impurity measure should do. Now we can either use the same formula to calculate the entropy for bank 2 or bank 3, or we can use this graph as a lookup table for bank 2 and bank 3. In this case, for bank 2, the probability of bad is 0.4. So if you come here, look at 0.4, you can see the entropy is 0.97. And similarly for bank 3, the PB is 0.9. So if you come here, then you should find the entropy is 0.47, which is exactly the same as bank 1 as we expected, because this entropy graph is symmetrical. Now I want you to pause the video again and do a quick calculation to see if you get to the same numbers. We're now ready to move to the discussion of classification with one attribute. So for bank 2 car members, let's assume we now have 2 attributes available on each car members: social security number and monthly income. In the introductory lecture, we attempted to make 2 separate scatter plots on them against the target variable. So similarly here, if we assume instances are evenly spaced with respect to social security number and monthly income, we should see the 2 scatter plots looks something close to what we have here. Now, since social security number is not predictive, the proportion of bad to goods stays the same along this axis. Therefore, if we zoom in with a window like this, and we move the window along the axis like this, within those subspace, the impurity stays the same, i.e. the same entropy as the whole population, the whole data set within those subspace. It's different for the monthly income because the proportion of bads to goods decreases along the monthly income axis. Therefore, if we zoom in with a window like this, the entropy within the window should be different from the entropy for the whole data set. So if we move the window this way, the first window and the third window both should have a lot smaller entropy than 0.97 as the whole data set. Let's now take a closer look at the monthly income scatter plot. Let's find a monthly income value that divides the higher 50 from the lower 50 in terms of monthly income. Let's call these 50 instances on the left the low income segment, and the 50 instances on the right the high income segment. So now their bad to good proportions have changed and are represented as the two new pie charts below. Now the probability of bad for the low income segment becomes 34 here divided by 50, which is about 68%. The probability of bad for the high income segment is now 6 divided by 50. That comes to 12%. Now I can apply the same formula that we just introduced earlier to recalculate the entropy within each of the two segments, and it comes to 0.9 for the low income segment and 0.53 for the high income segment. Both of them are lower than the entropy for the whole data set. Now, if we want to calculate the combined entropy of the two segments, it seems reasonable to multiply this by half, because this is the entropy of half of the population, half of the data set, half of the original data sets. And then it seems reasonable to do the same on the high income segment, i.e. I would multiply 0.5 by 0.9 to indicate half of the population, half of the data set had this entropy, and the other half has this entropy, 0.53 times 0.5. And that should give you a number that's close to 0.72. So now we can make a statement such as, with using the monthly income to divide the data set into two segments, the resulting entropy becomes 0.72, which is a lot lower than 0.97 without the knowledge of the attribute monthly income. Now we are ready to introduce another important concept in data science, the information gain. So let's quickly recap what we have done in the previous few slides. We calculate the entropy for bank 2 without any attribute available to be 0.97. Again, entropy is a numeric value, indicates the impurity of the target variable. Now with the information, with the attribute of monthly income, we are able to divide the data set into two segments, and we calculated the combined entropy, and it comes to 0.72. Now, the definition of information gain is simply the difference of the two. You have 0.97 to begin with, and you have 0.72 with the information of monthly income. Therefore, the difference is 0.25, which is defined as the information gain for the target variable because of the attribute monthly income. Now again, so what we have done here is really based on the insight that we mentioned earlier. The insight we mentioned earlier is, if we can quantify the impurity of a target variable, which we use entropy to accomplish that, then the amount of impurity that an attribute can reduce on the target variable can measure its information on the target variable, which is the notion of information gain. So now we are in a place to answer the second question we raised in the beginning: how to predict the target variable with only one attribute. The answer will be, if you have a number of attributes to select from, you should select the one attribute with the highest information gain because it provides the highest predictive power, which is an example of a larger topic, attribute selection. Hopefully we will have time to come back to talk more about attribute selection in future lectures. So now let's next turn to investigate how this information gain of 0.25 can help us in terms of prediction accuracy. We worked out this confusion matrix earlier for prediction for the bank 2 without any attributes. We predict by going with the majority, therefore we predict everyone to be goods, and the accuracy is at 60%. Now with the attribute of monthly income, we are able to segment the sample into two equal halves, the low income segment and the high income segment. So for each segment, since we have no further attributes, we'll learn also to go with the majority for prediction. Therefore, we predict all the low income segments as bad accounts, and we predict all the high income segment as good accounts. Now we need to work out two more confusion matrices, each for one of the two segments. Now I want you to pause the video again to give yourself a few minutes to work out this confusion matrix for the low income group and this confusion matrix for the high income group. So once you get these two confusion matrices correctly separately, we just need to add the two together to get a final combined confusion matrix. So this will be 34, 16, 6, 4, 4. So this should give you 50. This should also give you 50. This should give you 40. This should give you 60. And we can quickly verify to see whether this confusion matrix makes sense or not. So in this case, we predict half of the car member as bad accounts. We predict the other half as good accounts. Therefore, along the prediction dimension, you have 50 and 50. And in actual outcomes, we know we have 40 actual bad accounts. We have 60 actual good accounts. So things adds up well here. Now we can calculate the accuracy based on this new combined confusion matrix, which will be 34 plus 44 divided by 100. Again, these two numbers are the main diagonal numbers. These are the correct predictions. So it comes to 0.78, which is a higher accuracy compared to the previous 60% accuracy. Now we are ready to answer the third question I raised in the beginning of this lecture, which is how to classify the target variable with multiple attributes. So the keyword is recursive thinking. So imagine if we have done the segmentation here based on the monthly income. So imagine we have more attributes that are available for classification. Then what you need to realize is that I just need to treat a segment as if it's the data set we begin with, and then we repeat the same process. Within this segment, we use the information gain to find the most predictive attribute, or the one with the highest information gain, and then again we will split this segment into further subsegments, and within the subsegments it should have a lower impurity measure, i.e. a lower entropy, and that should allow us to further improve our prediction accuracy. This process is referred to as the tree induction. The tree induction for classification. Because if you repeat this recursive process a few steps, you're going to create an inverted tree structure. And then we call all the nodes at the bottom of the tree the leaf node. Then within the leaf nodes, you would apply going with the majority to predict all the instances that fall into those leaf nodes. So this concludes our lecture on the first part of predictive modeling.